I'm going to be pretty honest with you. The first half of this is pretty boring, but useful stuff. The second half is more interesting. And I've cut out a bunch of stuff from this section that I didn't want to talk about anyway. So you can check it out in the book if you want the full information. Otherwise, here's what I think you should know. So we're going to start off by saying that union and intersection, union meaning like either what's in either set, intersection what's in both sets, both unions and intersections are three things that you may or may not have heard before, but that does apply to like addition and stuff. They're commutative, they're associative, and they follow the distributive property as well. So all this means, commutative just means the order in which you union or intersect things doesn't matter, right? So this is the same as that. Addition is also commutative, right? 2 plus 3 is the same as 3 plus 2. Is subtraction commutative? Subtraction is not commutative, right? Because 2 minus 3 is not the same as 3 minus 2. So not everything is commutative. Division is also not commutative, but multiplication is. But union and intersections are both commutative. They're also both associative. And what that means is essentially the order on which you do things doesn't matter. So whether you take A union B and then union that with a third set, or whether you do A union, the union between B and that third set, it doesn't matter. And again, same with intersection. So here's like the order in terms of the order that you write them. Here, the order doesn't matter in terms of like what you do first out of three things. Distributive, you probably already know. You probably know that one from just regular math. But that says that if I have a union, the intersection of B and C, we can just do that in pieces. The union of A and B intersected with a union of A and C. This one's a little harder to see why it's true, but we're going to be giving some practice to see it being true. And it's also true in the other direction as well. The intersection of A and B union C is the intersection of A and B union the intersection of A and C. Okay. So these are the three properties. This is the boring half of this video. It's good practice to verify some of these, and we're going to be doing a little bit with some of these as well. The last thing I want to talk about for laws that I'm going to cover is also De Morgan's laws. Okay. And this one is a little bit less. So let's say this is number 1 is those three things. Number 2 is going to be De Morgan's laws. You may have seen this in a probability or statistics class as well. I don't actually cover it in mine, but I think a lot of people do. But yeah, De Morgan's laws are basically shortcuts. You don't need them, but they can save you some time. And there's kind of 2 of them. It says, if we're looking at A union B, and we want to take the complement of that. Well, that's A complement and B complement, but we no longer take their union. It flips to their intersection. So what this really means, right, is not A or B means not A and not B. Okay, which makes a little bit more sense, right? If you're not a vegetable or a fruit, then you are not a vegetable and you are not a fruit. Okay, and it goes the other way as well, right? Not A and B would be not A, union, not B. All right. If you're not both, then you must essentially be failing one or the other. Those are De Morgan's laws. Useful shortcuts. Again, you don't really need to have them memorized, but they can save you time. And again, I just think like in logic as well, and we're going to see this more in our chapter that we do on logic. In logic, this is a useful shortcut. Can also be like various ways of like writing logical processes in coding as well, in my opinion. I've done that a few times, but yep, they're useful to have. Let's do some examples, and that'll be this video. So, example, let's use the C and the D from before. So remember C was just the numbers 1, 2, 3, 4, and 5. Let's say D, remember, was 1, 3, 5, 7. And let's introduce a new set E. Let's have E be, what do I want E to be? I wrote it down somewhere. 1, 10, and 100. All right, and I have some questions for you here. Question is, I'm not actually going to do this in the video. Well, maybe I'll do one of them. Show that these are commutative, associative, and follow the distributive property. I'll show the distributive property, but this is good practice, right? So, and I'm not going to do all the proof, but just part of the proof, right? But one of the ways to see that the distributive property does work is this was one of the things that we would need to check. C intersect D union E should equal, right, what we want. We want the, I'll actually write it this way. We want to show that this is equal to C intersect D union C intersect E. So we always do our good proof writing. We don't start with what we want to prove, or we don't assume what we want to prove, right? We start with one side and we show it equals the other side. So what is that left-hand side? Well, that's C intersected with, well, what's D union E? D union E is what is in one or both of them. So it's going to be 1, 3, 5, 7, 10, and 100. Right? That's D union E. That's what happens when we combine these two sets. We never write duplicates. Well, what is in both this set and this set? The number 1, 3, and 5 is in both sets. So that's what the left-hand side equals. And the question is, does that also equal the right-hand side? Well, let's look at the right-hand side. What is C intersect D? What is in both of these sets? Well, it's 1, 3, and 5. Now we need to union that with what's in both C and E. What's the overlap between C and E? The only overlap between these two sets is element 1. Be very careful to write the set containing 1 and not just 1. Right? These two things are different. Okay? Now we union these two sets. And again, we're going to get 1, 3, and 5. And you can see, hey, look. These equal each other. The left-hand side equals the right-hand side. So we see that this distributive property is holding in this case. All right, and you could check it with the other direction. You could check it with other pairs of sets. It's a good idea to pause the video and try to show commutativity and associativity as well. Those are a little bit more basic. Commutativity is pretty much useless. It's trivial, but associative would at least take some steps and could be some good practice if you want it. I'm not going to do it though. All right, the second thing I also want you to do is calculate. Let's use De Morgan's laws. So someone's car alarm is going off. I want you to calculate C union D complement both ways, with and without De Morgan's laws. So pause the video, do that out. And then again, you can skip forward to see if we get the same answer, or you can stick around for the walkthrough. But again, there's two ways of doing this. There's the way of doing it directly. So again, C union D complement is the complement of C union D. What is C union D? It's what's in both sets. It's 1 through 5 and the number 7. 1, 2, 3, 4, 5, 7. Okay. Now the total complement of that is everything that's a natural number, everything that's in omega. I didn't specify it, but omega is going to be n just like last time. What are all the natural numbers that are not in this set? Well, 6, 8, 9, 10, and every other natural number in that direction. So let's see if De Morgan's laws holds. This is supposed to be not C intersect not D, according to De Morgan's laws. So what's not C? Everything that's not in C is the natural numbers that are 6 or higher. So 6, 7, 8, etc. We intersect that with not D. What's in the complement of D? That's 2, 4, 6, 8, and then all the natural numbers after that. So now we go 9, 10, 11, etc. And we need to take the intersection of these two sets. So what is in both of these sets? Well, 6 is in both of these sets. 8 is in both of these sets. So is 9 and 10. This is what's in both of these sets. So when we take the intersection, we get 6, 8, 9, 10. And would you look at that? These are the same, just like we wanted. Good job, De Morgan. You did good today. And every day. Well, every day, this law. I don't know what else De Morgan did. But yeah, that'll always be the case. Let me know if you have any questions. That's everything I wanted to do in this video. We had to break down 2.9 into 3 videos because some of this guy's chapters are like this long, and then this one was like 5 pages or something. But yeah, hopefully you have a good one. Take it easy.